The ISC engine utilizes the all-new CAPS fuel system. This system was developed to provide the higher injection pressures needed for the Cummins C-Series engine. The parts of the system are serviced and warrantied by the Cummins system. The CAPS fuel system provides for full electronic control of injection pressure, timing, and fuel quantity, delivery curve shaping, high peak injection pressures, high fuel pressure at low engine speeds, as well as fuel pressure independent of engine speed. The system also provides for emissions compliance, fuel economy, drivability, and offers a variety of customer features, such as electronic timing, to give improved emission, fuel economy trade-offs, cruise control, customized torque curves, and road speed limiting. An additional benefit of the CAPS system is that it allows electronic control of injection pressure and allows the injection pressure to be high at low engine speeds. This provides for better transient response, better low-speed clutch engagement torque, and higher peak torque. The CAPS concept is a high-pressure fuel pump. The high-pressure pump pressurizes an accumulator that in turn is connected to a single injection control valve. The injection control valve sends fuel to a distributor where it is directed to the individual injectors. The ISC engine utilizes a 12-volt DC electric lift pump controlled by the ECM and has a minimum operating pressure of 10 psi. The self-priming lift pump fills the low-pressure side of the fuel system. When the key is first turned to the on position, the lift pump operates for approximately 30 seconds, regardless of whether the engine is running or not. The CAPS fuel injection pump contains a gear pump which pulls the fuel from the tank after the system has been primed by the lift pump. After the initial 30-second cycle, if additional fuel priming is necessary, the key switch must be cycled from the on position to the off position and then back on to restart the lift pump. A check valve in a separate fuel supply passage allows the CAPS fuel injection pump to bypass the lift pump and pull fuel from the tank upon demand, even when the lift pump is operating. An optional fuel heater maintains fuel temperature in cold weather to improve fuel flow and prevent waxing. The fuel heater is wired through a relay and is continuously powered when the vehicle key switch is in the on position. Fuel heater circuit current decreases as the fuel temperature increases until it reaches a minimal milliamp current flow. The ISC engine uses a convenient combination fuel filter water separator. The filter uses a Stratapore 10-micron filtering media, a water-in-fuel sensor, and a water drain. The filter causes water to precipitate out of the fuel and drip to the bottom of the housing. When the sensor becomes immersed in water, the whiff sensor alerts the operator to water in the fuel filter housing. The fuel pump drive gear is driven at half engine speed by the cam gear. Keying the fuel pump drive gear to the fuel injection pump shaft and aligning the timing marks to the camshaft provides a positive location for fuel injection pump installation and simplifies timing. The CAPS fuel injection pump is the heart of a new electronic fuel system available for ISC engines. In addition to other sensors, CAPS can compensate for temperature rises in the incoming fuel to maintain constant engine power. The fuel pressure temperature sensor, located at the rear of the accumulator, senses the temperature of the fuel in the accumulator. Constant fuel delivery is provided by fuel compensation at high and low temperatures. The Bosch injectors used on the ISC engine are a hole-type nozzle design. 4 different flow rate injectors are used throughout the ISC horsepower ranges. An O-ring seal on the injector body separates the fuel manifold from overhead engine oil. A 1.5 mm sealing washer is installed on the injector tip to seal the cylinder. This washer establishes the vertical position of the injector for alignment with the high-pressure fuel connector. The injectors are located under the rocker cover between the rocker levers and are installed in the center of the combustion chamber. The shape of the rocker levers allows the injector to be removed without disturbing the rocker adjustment. The slot in the top of the injector and the hold down are offset to orient the injector in the correct direction. This ensures that the supply hole in the injector is aligned with the fuel connection that allows the fuel to flow from the high-pressure fuel lines. In this section, we will look at the fuel flow through the ISC engine. Keep in mind that the fuel also provides some lubrication and cooling effect within the fuel system. The electric fuel lift pump, mounted on the side of the engine, draws fuel from the fuel supply tank and primes the fuel system. Fuel flows through the externally mounted filter head and into the combination fuel filter water separator. This filter is a 98.7% efficient 10-micron filter. After water and contaminants are removed, the filtered fuel is transferred to the gear pump section of the fuel injection pump through the low-pressure supply line. The CAPS fuel injection pump is made up of 5 separate modules: gear pump, camshaft and housing, accumulator, injection control valve, and distributor. Let's take a look at each of these modules to become familiar with the major components of the pump, beginning with the gear pump module. The major components of the gear pump module include the gear pump housing, oil seal, fuel seal, pumping gears, piston and spring-style pressure regulator, fuel pump inlet fitting, gear pump drive shaft, bushings, rear coupling, and front coupling. The next module contains the camshaft and housing. This module includes the camshaft housing, O-ring seal, camshaft, tapered roller bearings, and tappet assembly, including rollers, bronze pins, and tappet housing. The accumulator module includes the 2 high-pressure pumping assemblies, consisting of a plunger, spring, spring retainer, barrel, and barrel retainer. Pressure control valves, or PCVs. Hardened steel accumulator. High-pressure accumulator check valves. Rate shape snubber. Seal disc. Pressure temperature sensor. Rate shape tube and mounting isolators, and air bleed valve. The injection control valve module contains the housing with supply, distributor, and drain ports, seal plate with crush tubes, inner and outer control pins, stator, and fuel return pressure regulator assembly. The distributor module contains the distributor housing, rotor with titanium nitrate coating, rate-shaped tube connection and seal disc, 6 injector snubber valves and seal discs, and the rotor coupling. Fuel flow in the pump begins as fuel enters through the inlet tube on the outboard side of the fuel injection pump. The fuel first travels to the gear pump module. The gear pump assembly is driven by the fuel pump drive gear through the fuel injection pump camshaft located in the camshaft housing. As the gears rotate, they generate the fuel pump housing pressure. From the gear pump, the fuel is sent through a 100-micron screen at the outlet side of the gear pump. The gear pump generates maximum gear pump pressure at engine speeds of approximately 1100 RPM and above. The pressure regulator controls this pressure to approximately 165 psi. Excess fuel pressure is directed back to the inlet side of the gear pump. Internal drillings in the housing direct fuel flow to the two pumping control valves, or PCVs. When the PCVs are de-energized, the fuel flows through the valves into the two high-pressure pumping plunger chambers. The position of each of the ceramic pumping plungers is controlled by a lobe on the camshaft. Two cam lobes with 3 lift profiles per lobe are in contact with the two pumping plungers through roller tappets which ride on the cam. The cam lobes and roller tappets are a micro-finish complex crown roller design. When the camshaft moves to its inner base circle and allows the plunger to retract, the gear pump pressure fills the chamber and forces the plunger to the bottom of its travel against the spring retainer. The camshaft, turning at 1/2 engine speed, then pushes up on the tappet assembly, which in turn forces the pumping plunger to travel up in its bore. As the plunger starts to lift, the fuel in the pumping plunger chamber pushes back through the PCV. When the PCV is energized, it closes off the flow path back through the valve, and the remaining fuel is trapped in the pumping chamber. As the plunger continues to move up, pressure in the pumping chamber rapidly increases until it is high enough to overcome the accumulator check valve. This check valve is held shut by the fuel pressure stored in the accumulator until the pumping pressure exceeds the accumulator pressure. The fuel then pumps into the accumulator until the plunger reaches the top of its travel. Once the PCV has been energized, the pressure in the pumping chamber holds the valve shut against its seat. Prior to TDC of the plunger stroke, the PCV is de-energized. The de-energized valve opens only after the plunger begins to retract. As the plunger continues to retract, fuel flows through the open PCV and again fills the pumping chamber. The timing of when to close the PCV is controlled by the ECM, using input from the fuel pressure sensor, which senses the accumulator pressure. The ECM has algorithms to determine when to shut the PCV to achieve the correct accumulator pressure before the next injection event. The PCVs are factory installed and flow tested with the assembly to verify proper seating. Therefore, these valves cannot be replaced in the field. An air bleed fitting on the top of the accumulator housing bypasses some fuel flow to the fuel tank and allows any air in the system to be bled off. Fuel is bypassed to this fitting through a drilling from the gear pump supply. A small orifice controls the fuel flow through this fitting. An additional connection to the barrel and plunger exterior provides hydraulic balance and lubrication. Once the fuel enters the accumulator, it remains stored in the 6 connected chambers until needed for injection. The accumulator contains a large enough quantity of fuel to prevent the injection pressure from dropping more than 10% during fuel injection. The fuel leaves the accumulator through the rate-shaped snubber valve. From the rate-shaped snubber, the fuel flows through the rate-shaped tube. The length and internal diameter of this tube is designed to control the early part of injection. This tube acts to limit the amount of fuel injected during the first few degrees of injection. A pressure wave in the tube causes the initial fuel flow to be reduced until the cylinder is ready for full combustion, thereby improving combustion efficiency. From the rate-shaped tube, the fuel enters the distributor module through the inlet fitting. Drilled passages in the distributor housing direct the fuel flow to the injection control valve. The injection control valve controls the flow of fuel through the supply, distributor, and drain ports. With the injection control valve in the closed position, the fuel source is shut off at the seat between the inner and outer pins. When the injection control valve stator is energized, the stator pulls the outer pin toward the front of the housing. Spring pressure causes the inner pin to remain in contact with the outer pin at the beginning of its travel. When the inner pin contacts its stop, the outer pin continues to move and a flow path is created between the inner and outer pins. At this point, the source is open to both the distributor port and the drain port. Because the drain port offers little resistance to flow, the pressure in the distributor port does not increase. Hydraulic action between the inner and outer pins causes the inner pin to move back against its spring pressure, further opening the flow path between the two pins. When the outer pin contacts its seat, the drain path is shut off, and pressure builds in the distributor rotor port. The fuel then flows through one of the 6 internal drillings to the high-pressure fuel lines. Additional drillings in the rotor transfer pressure to the opposite side of the rotor to help prevent side loading. When the injector control valve stator is de-energized, spring pressure on the outer pin causes it to push back off of its seat. This opens the flow path between the source, distributor port, and the drain port. With the drain port open, the pressure in the high-pressure fuel lines reduces quickly, allowing the needle to close, thereby ending injection. The regulator in the injection control valve drain allows flow to the drain line until the pressure drops below 330 psi. This drastically reduces the pressure at the nozzle until the next injection cycle. The snubber valve slows the pressure drop in the injection line. The outer pin continues to travel away from the stator, and when it contacts the inner pin, shuts off the flow path from the source. The outer and inner pin then move to their de-energized position for the beginning of the next cycle. By controlling the energizing and de-energizing of the injection control valve stator, the ECM controls injection timing and the quantity of fuel injected. Electronic and mechanical delays are taken into account as the calibration is designed. A transorb diode installed in the engine harness is wired in parallel with the injection control valve. This diode protects the ECM from spikes resulting from the collapsing magnetic field when the ICV is turned off. If the transorb diode fails in a shorting mode or an open mode, fault codes will result. A properly operating transorb diode will produce heat. Be careful not to touch the diode after the engine has been operating. There are 6 injector ports in the distributor housing, one connected to each of the 6 injection line snubbers. The port in the distributor rotor is large enough to assure that the port does not control the beginning or end of the injection, but that injection is controlled by the energizing and de-energizing of the injection control valve. Fuel flow travels out of the injection line snubber and enters into the fuel injection line. The 6 injection lines are connected to the pump to provide the desired 1-5-3-6-2-4 firing order sequence. The pumping cycle is repeated for each cylinder. The internal dimension, rigidity, and length of the high-pressure fuel lines is critical for proper fuel delivery. From the high-pressure fuel lines, the fuel travels to the fuel connector installed in the cylinder head. This connector provides a flow path between the high-pressure fuel line and the injector inlet. An edge filter installed in the fuel connector breaks down any debris remaining in the fuel before it enters the injector. The high-pressure connector to injector seal is maintained through the flare fitting on the connector and the angled seat on the fuel inlet port in the injector. The torque on the high-pressure fuel line fitting holds the connector in position. Bosch hole-type injectors are used on ISC engines. The injector assembly consists of the high-pressure inlet, nozzle body, shims, spring, needle valve, nozzle retainer, nozzle, and sealing washer. The fuel flows down the drilling in the nozzle retainer and nozzle and enters the needle valve bore. The spring load on the needle valve keeps the valve closed until the pressure rises to approximately 4,500 psi. At this pressure, the valve lifts to allow fuel to flow into the nozzle tip. The point at which the needle valve lifts is the operating pressure setting. This is often referred to as the pop pressure setting and is set by the shims placed above the spring. Due to the size restriction of the holes in the nozzle and the pressure amplification in the high-pressure fuel lines, the pressure continues to increase up to as high as 17,000 psi. During injection, the pressurized fuel is forced through the 7 spray holes in the injector nozzle, causing atomization of the fuel for combustion. When the injection control valve closes, the pressure in the nozzle rapidly reduces. When the pressure drops to approximately 60% of the opening pressure, the needle valve quickly closes. This action stops the flow of fuel into the cylinder and prevents exhaust gases from entering the nozzle. Fuel leaking past the needle valve drains through the spring cavity into the fuel drain manifold. This small amount of leak-off from the injectors flows to the injector drain manifold integrated as a drilling in the cylinder head. Fuel from the ICV pressure regulator valve and return fuel from the injector drain are combined, and return fuel flows to the fuel tank. An O-ring on the connector acts as an external seal for the fuel drain manifold. An O-ring at the top of the injector provides a seal between the engine oil and the fuel drain manifold. And a copper sealing washer provides the combustion chamber seal. The air bleed connects to the injection control valve drain and flows to the rear of the engine where it joins with the injector return. Note that more flow comes out of the accumulator than is injected. Some of the high-pressure pumping capability is lost to fuel leaks past the plunger, some to the trapped volume above the plunger, and some to accumulator check valve dynamics. Once the flow leaves the accumulator, some fuel leaks out the injection control valve, distributor, and injector. About 1/2 of the flow leaving the accumulator goes out the injector during injection.